Picture this. It's 3 a.m. at a research facility somewhere in the United States. A scientist is sitting at her desk, coffee gone cold, screen glowing in the dark. She's been staring at data for 6 hours straight. The data came in from the James Webb Space Telescope, the most powerful eye humanity has ever pointed at the cosmos. A machine that cost $10 billion to build. That took 30 years to design and develop. That carries within it the dreams and obsessions of thousands of scientists across multiple generations. And something in that data is wrong. Not wrong like a typo, not wrong like a miscalculation, wrong like the universe is not behaving the way it is supposed to behave. Wrong like every equation, every model, every framework built on the foundation of Einstein's work is pointing to something impossible. She calls her colleague calls another scientist, that scientist calls someone else. Within 48 hours, 12 of the brightest minds in cosmology are on a video call at 2 a.m. their respective time zones, all of them looking at the same data, all of them saying the same thing. This cannot be right, but it is. And what James Webb detected, what that telescope found out there in the darkness between galaxies, has not just created a scientific controversy. It has cracked open a question so enormous, so fundamental, so ancient in human thought, that most scientists are still afraid to say it out loud. In polite company, what if our universe is not the only one? What if there is something out there beyond the edge of everything we can see, beyond the boundaries of space and time as we understand them, another universe, with different rules, different constants, different physics? What if the James Webb Space Telescope just found the fingerprints of that other universe pressed against ours? Today we are going to go through all of it. Every piece, every discovery, every theory, every implication. We are going to start from the absolute beginning, from what the universe is, from who Einstein was and what he built, from what the James Webb Telescope is and why it matters. And then we are going to walk, step by step, through the discovery that is making scientists around the world lose sleep. By the end of this video, you will understand why this is possibly the most significant scientific moment of the 21st century. And you will understand why nothing, and I mean nothing, about our understanding of reality may ever be the same again. But before we begin, if space fascinates you, a like and subscribe means everything to us. Let's begin. To understand why James Webb's discovery is so shattering, you first need to understand what exactly it is shattering. And that means going back, all the way back to a young man sitting in a patent office in Bern, Switzerland, in the early 1900s. His name was Albert Einstein, and he was bored. Not bored in the way most people get bored. Bored in the way that only the most extraordinary minds get bored, where the boredom itself becomes fuel. Where the restless mind, unable to stop, starts asking questions that nobody else is asking. Questions that seem almost childish on the surface, but contain within them an abyss of complexity. Einstein's most famous childish question was this: what would it look like to ride alongside a beam of light? If you ran next to a beam of light at exactly the speed of light, what would you see? Would the light look frozen? Would it look like a standing wave? Would it look like anything at all? He sat with this question for years, playing with it in his mind, turning it over, examining it from every angle. And in 1,905 inches, what historians of science call his miracle year, he published 4 papers that each individually would have made him the most famous physicist of his generation. Together they rewrote the foundations of physics. The most famous idea to come out of that period was special relativity. And special relativity said something that seemed absolutely insane when Einstein first proposed it. It said the speed of light is constant, always, for every observer, no matter how fast they are moving. Think about what this means. If you are standing still and a ball rolls past you at 10 kilometers per hour, you see it moving at 10 kilometers per hour. If you are running alongside that ball at 5 kilometers per hour, you see it moving at 5 kilometers per hour relative to you. Speed is relative. Speed depends on the observer. This is just basic common sense. This is how Newton described the world. This is how the world works. But light doesn't do this. If you are standing still and a beam of light passes you, It moves at 299,792,458 meters per second. If you are flying in a rocket at half the speed of light toward that beam, it still moves at 299,792,458 meters per second relative to you. Not faster. Exactly the same. This violates common sense completely. And Einstein didn't just say, okay, this is weird. Let's note it down. He said if the speed of light is constant for all observers, then everything else we thought was constant must actually be variable. Time itself is not constant. Time runs at different speeds depending on how fast you are moving and how strong the gravitational field around you is. Space itself is not fixed. Distances change. Lengths contract. The geometry of the universe is not the rigid flat grid that Newton imagined. Mass and energy are interchangeable. They are different forms of the same thing. E equals mc squared, the most famous equation in human history, meaning a tiny amount of mass contains an incomprehensible amount of energy. And then, in 1915, 10 years after special relativity, Einstein went further, much further. He published general relativity, and general relativity changed everything. Most people have heard of general relativity. Very few people understand what it actually claims about the nature of reality. Let me try to explain it as clearly as possible. Before Einstein, scientists following Newton thought of gravity as a force, an invisible pulling force between objects that have mass. The sun pulls the earth pulls the moon. You pull the ground beneath your feet and the ground pulls you back. Newton's equations for gravity worked incredibly well. They let us predict planetary orbits with extraordinary precision. They let us understand tides. They let us calculate the trajectories of cannonballs and eventually rockets. But Newton himself admitted he did not know what gravity actually was. He knew what it did. He did not know what it was. Einstein answered that question, and the answer was reality bending. Einstein said gravity is not a force at all. Gravity is the curvature of space-time. And space-time is a single four-dimensional fabric, 3 dimensions of space woven together with 1 dimension of time that makes up the structure of the universe itself. When a massive object like the sun sits in space-time, it curves that fabric, like a bowling ball placed on a stretched rubber sheet. The sheet dips around the bowling ball. Other objects moving through that curved region, like the planets, follow the curves in the fabric. And from our perspective, that curved path looks like they are being pulled toward the Sunday. But they are not being pulled. They are following the geometry of space itself. This is general relativity. And the implications of this single idea are staggering. They keep unfolding even today, more than 100 years later. General relativity predicted that massive objects would bend light. Einstein calculated that a star's light passing near the sun should appear to shift position because the sun curves the space-time that the light travels through. In 1919, during a solar eclipse, British astronomer Arthur Eddington measured the positions of stars near the Sunday, and they were shifted, exactly as Einstein had predicted. That measurement made Einstein world famous overnight. Suddenly, this patent office clerk who wrote strange papers was on the front page of every newspaper on Earth. General relativity predicted that time runs slower in stronger gravitational fields. This is called gravitational time dilation. And today your GPS system has to correct for this effect constantly. The clocks on GPS satellites run very slightly faster than clocks on the Earth's surface, because they are higher up in a weaker gravitational field. If engineers didn't account for this, GPS would drift by kilometers per day. General relativity predicted the existence of black holes regions where space-time is so extremely curved that nothing, not even light, can escape. Einstein himself found this result so disturbing that he didn't believe it. But black holes turned out to be real. Spectacularly, terrifyingly real. General relativity predicted gravitational waves, ripples in the fabric of space-time itself caused by accelerating massive objects, like 2 black holes spiraling toward each other and merging. In 2015, exactly 100 years after Einstein published general relativity, the LIGO detector felt those ripples for the first time. The universe was literally shaking, and we felt it. And general relativity, when applied to the universe as a whole, made perhaps its most dramatic prediction of all. The universe cannot be static. It must be either expanding or contracting. Einstein himself was so disturbed by this result that he added a fudge factor to his equations, what he called the cosmological constant, just to make the universe stand still on paper. He later called this the biggest blunder of his life, because in 1929, astronomer Edwin Hubble looked through his telescope and confirmed what Einstein's equations had always been screaming. The universe is expanding. Galaxies are moving away from us, and the farther they are, the faster they are receding. The universe is getting bigger, in every direction, all the time. And if you run that expansion backward in time, like rewinding a film, everything in the universe was once in the same place. Everything. All of space, all of time, all of matter and energy was compressed into a single point of infinite density. And then approximately 13.8 billion years ago it wasn't. The Big Bang. The moment when space itself began to expand. When time itself began to tick. When the laws of physics first switched on. This is the universe we live in. This is what general relativity describes. And for 100 years this framework has been tested against observation after observation after observation, and it has passed every single test, until James Webb. But before we get to the telescope, we need to understand one more thing, one more concept that has been quietly building in theoretical physics for decades. A concept that most mainstream scientists once dismissed as untestable fantasy. The multiverse. The multiverse is not a new idea, but it has always existed at the uncomfortable edge of respectable science. The problem is, this science is built on a very specific principle. The principle of falsifiability. An idea is scientific only if you can, at least in principle, test it. If you can make a prediction that could turn out to be wrong, if there is some observation that could prove the idea false. For decades, the multiverse failed this test spectacularly. If there are other universes, how would we know? If they are completely separate from ours, if no signal, no light, no particle can travel between them, then they are undetectable by definition. And something that is undetectable by definition is not a scientific theory. It is philosophy, it is metaphysics. It might be beautiful, it might even be true, but it is not science. And so most physicists kept the multiverse at arm's length. They would discuss it at conferences, they would write papers exploring its theoretical implications. But they were always careful to add the caveat, this is speculative. We cannot test this. We don't know. But there were several serious theoretical reasons why the multiverse kept coming back, why it refused to be dismissed. The first was the fine-tuning problem. Here is something that should keep you up at night. Our universe has a set of fundamental constants, numbers that govern how physics works, the strength of gravity, the strength of the electromagnetic force, the mass of the electron, the speed of light. The cosmological constant that governs how fast the universe expands. These constants are not predicted by our theories, they are simply measured. We observe them, we plug them into our equations, and our equations work. But here is the terrifying part. If any of these constants were even slightly different, if you changed the strength of gravity by a fraction of a percent, or tweaked the mass of the electron just slightly, or adjusted the cosmological constant by a tiny amount, the universe would be completely, utterly, totally incompatible with life. Not just incompatible with human life, incompatible with any complex structure at all. If gravity were a little stronger, the universe would have collapsed back on itself seconds after the Big Bang. No galaxies, no stars, no planets. If gravity were a little weaker, matter would never have clumped together. No galaxies, no stars, no planets. If the cosmological constant, the energy of empty space, were a tiny bit larger, the universe would have expanded so fast that no structure could ever have formed. Pure, cold, empty, expanding void. If the strong nuclear force, the force that holds atomic nuclei together, were slightly weaker, atoms wouldn't exist. Hydrogen would never fuse into helium. Stars couldn't ignite. No energy. No light, nothing. The universe is extraordinarily, suspiciously, almost impossibly fine-tuned for the existence of complex structures, chemistry, and life. Why? There are essentially three possible answers. First answer, coincidence. We just got incredibly lucky. The universe happened to have exactly the right constants by pure chance. This is technically possible, but feels deeply unsatisfying. The probability is so astronomically small that many scientists find this explanation worse than no explanation at all. Second answer: design. Some intelligence set the constants deliberately. This is the domain of religion and philosophy, not science. Science cannot test this. Third answer: the multiverse. If there are an enormous number of universes, perhaps an infinite number, each with different values for the fundamental constants, then it is no longer surprising that at least one of them has the right values for life. We exist in this one precisely because this is the one where existence is possible. This reasoning is called the anthropic principle. The multiverse turns a miraculous coincidence into a statistical inevitability. And this is why serious physicists kept thinking about it, even as they acknowledged they couldn't test it. But there was another route to the multiverse, one that came not from philosophy but from the detailed physics of the early universe. And it is called cosmic inflation. In the 1980s, a physicist named Alan Guth proposed a solution to several deep problems with the standard Big Bang model. The standard Big Bang model had some things it couldn't explain. Problem 1. The horizon problem. When we look at the cosmic microwave background, the leftover radiation from the early universe, the oldest light we can see, it is almost perfectly uniform in temperature in every direction. The temperature variations are less than 1 part in 100,000. But here's the puzzle. Regions of the early universe that are on opposite sides of the sky, opposite ends of the observable universe, could never have been in contact with each other. They were too far apart. Even light couldn't have travelled between them in the time available. So why do they have the same temperature? How did they coordinate? How did they reach thermal equilibrium if they could never communicate? Problem 2. The flatness problem. The geometry of the universe, the large-scale shape of space-time, appears to be almost perfectly flat, not curved like a sphere, not curved like a saddle. Flat. Like an infinite plane. For the universe to be this flat today, at the moment of the Big Bang, it would have had to be fine-tuned to flatness with extraordinary precision. Even a tiny deviation in the early universe would have grown over billions of years into a universe that either collapsed immediately or expanded so fast it would be empty. The universe appears almost impossibly flat. Guth's solution to both problems was elegant and radical. He proposed that in the first fraction of a second after the Big Bang, an incredibly tiny fraction, something like 10 to the power of negative 36 seconds, the universe underwent a period of exponential expansion. Not the ordinary expansion that continues today, not the kind that doubles the size of the universe over billions of years. Explosive, violent, incomprehensibly rapid expansion. In this blink of an instant, the universe grew by a factor of something like 10 to the power of 26 or more. A region smaller than a proton inflated to something larger than a galaxy. This is cosmic inflation. And it solved the horizon problem because all the regions we see were once in contact before inflation separated them. And it solved the flatness problem because any curvature in the initial geometry would be stretched out by inflation until it was effectively flat, just as the surface of a balloon looks flat when you blow it up enormously. Inflation fit beautifully with observations. The pattern of tiny fluctuations in the cosmic microwave background matched inflation's predictions remarkably well. Inflation became part of mainstream cosmology, but inflation came with a consequence that many physicists found deeply uncomfortable. If the quantum field that drove inflation, called the inflaton field, is the way theorists think it is, then inflation doesn't just happen once. Inflation is eternal. Different regions of space inflate at different times. Some regions stop inflating and become universes like ours. Other regions keep inflating and eventually spawn other universes. This is called eternal inflation. And eternal inflation implies that our universe is one bubble in an infinite foam of universes, each bubble a separate space-time, each bubble potentially with different physical constants, an infinite landscape of universes. This is the most scientifically grounded version of the multiverse, and it predicts something potentially testable. If our universe is a bubble in that foam, and if other bubble universes exist nearby, then in the early universe, our bubble could have collided with another bubble, and that collision could have left a mark. A bruise in space-time, an imprint in the cosmic microwave background, a signal. Something that James Webb might be able to see. Before we get to the discovery, you need to understand the instrument that made it possible. Because the James Webb Space Telescope is not just a bigger, better version of the Hubble. It is a fundamentally different kind of machine, built to see things that nothing built before could see. Built specifically to look at the universe in its earliest moments. To look back in time as far as physics allows us to look. Let's start with the basics. The James Webb Space Telescope, JWST, launched on December 25, 2021, Christmas Day, and it was perhaps the most nerve-wracking launch in the history of space science, because JWST had to be folded up like an incredibly complex origami to fit inside the rocket, and after launch it had to unfold itself in space. A sequence of 344 single points of failure. 344 things that had to work perfectly in sequence. If any one of them failed, the $10 billion telescope, the 30-year project, the dreams of thousands of scientists would be dead. Every single one of them worked. JWST traveled to a point called the second Lagrange, point L2, about 1.5 million kilometers from Earth. This is a gravitationally stable point where the telescope can orbit the Sun at the same rate as Earth, always keeping Earth, the Moon, and the Sun behind it, always shielded from their light and heat. And this brings us to what makes JWST so different. JWST observes primarily in infrared light, not visible light, infrared. Why infrared? Two reasons. First, the early universe. As the universe expands, light from distant objects is stretched. The farther something is, the more its light is stretched toward the red end of the spectrum and then into the infrared. The very earliest galaxies, the ones that formed just a few 100 million years after the Big Bang, have their light so stretched that it is only visible in infrared. Hubble could not see these galaxies in detail. JWST can. Second, dust. Much of the most interesting activity in the universe, star formation, galaxy evolution, planet formation, happens inside clouds of gas and dust that are opaque to visible light. Infrared light penetrates dust. JWST can see through the cosmic fog to the processes happening within. JWST's primary mirror is 6.5 meters in diameter. Compare that to Hubble's 2.4 meters. But it's not just about size. The mirror is made of 18 hexagonal segments of gold-coated beryllium, each independently adjustable to nanometer precision. The total light collecting area is more than 6 times that of Hubble. JWST also carries a 5-layer sun shield the size of a tennis court made of kapton, a material about as thin as human hair that keeps the telescope at temperatures below -233 degrees Celsius. Cold enough that its own infrared heat doesn't swamp the faint signals it is trying to detect. The telescope has 4 main scientific instruments: a near-infrared camera, a near-infrared spectrograph, a mid-infrared instrument, and a fine guidance sensor with near-infrared imaging capability. Together, these instruments can image the universe across a vast range of wavelengths, take spectra of individual objects, and analyze the chemical composition of distant atmospheres. JWST was designed with one ultimate goal: to see the first light, the first galaxies, the first stars, to look back to the beginning of everything and understand how the universe we see today emerged from the chaos of the Big Bang. What it found, in the process of trying to do this, was something nobody expected. Something that the standard model, the Lambda-CDM model, that has been cosmology's gold standard for decades, says should not exist. Before we talk about what broke the model, we need to understand what the model is. The standard model of cosmology is called Lambda-CDM. Lambda stands for the cosmological constant Einstein's fudge factor, which turned out not to be a fudge at all, but to represent the energy of empty space, dark energy. CDM stands for cold dark matter. Lambda-CDM describes a universe that began 13.8 billion years ago in the Big Bang. In the beginning, the universe was an incredibly hot, dense, perfectly uniform soup of energy. As it expanded and cooled, matter condensed. First hydrogen and helium nuclei formed. Then, about 380,000 years later, the universe cooled enough for electrons to bind to nuclei and form neutral atoms. The universe became transparent. Light could travel freely for the first time. That released light is what we see today as the cosmic microwave background. After that, gravity took over. Regions that were slightly denser than average attracted more matter. Small fluctuations grew. Gas clouds collapsed. The first stars ignited massive, short-lived, made almost entirely of hydrogen and helium. They burned bright and died fast, seeding the universe with heavier elements through supernova explosions. Then galaxies formed. Clusters of galaxies, superclusters, the cosmic web we discussed earlier. This whole process was shaped by two invisible components. Dark matter, which doesn't interact with light but has gravity. It formed the scaffolding, the invisible skeleton around which normal matter assembled into galaxies. Without dark matter, galaxies as we see them could not have formed. They would have been too diffuse, too scattered, too disorganized. And dark energy, which acts against gravity on large scales, accelerating the expansion of the universe, preventing everything from collapsing back in on itself. Lambda-CDM describes all of this with remarkable precision. It makes specific, quantitative predictions about how many galaxies of what sizes should exist at what distances, about how clustered matter should be on different scales, about the precise pattern of the cosmic microwave background. And for decades, every observation confirmed it. The Sloan Digital Sky Survey mapped millions of galaxies. Lambda-CDM predicted their distribution, match. The Planck satellite measured the cosmic microwave background with extraordinary precision. Lambda-CDM predicted its pattern, match. The distribution of galaxy clusters across cosmic time, the ratio of different kinds of matter, the rate of expansion of the universe, match after match after match. Lambda-CDM seemed rock solid. And then James Webb started sending data. The first indication that something was wrong came quickly, almost embarrassingly quickly after JWST started operations. Within months of getting its first science data before most scientists had even processed the novelty of what they were looking at, a deeply uncomfortable pattern started emerging. JWST was seeing galaxies. Very early galaxies. Galaxies from the first few 100 million years of the universe, a period that had never been seen in such detail before. And there were too many of them. Not slightly too many, massively too many. Lambda-CDM makes specific predictions about the early universe. It says that in the first billion years after the Big Bang, galaxies were small and relatively sparse. Structure formation took time. Gravity needed to work slowly, assembling matter piece by piece. The first galaxies should be small, irregular, not very massive, not particularly luminous. JWST found galaxies that were fully formed, massive, bright, and structured when the universe was only 300 to 600 million years old. Let me put that in perspective. The universe is 13.8 billion years old. These galaxies existed when the universe was just 2 to 4% of its current age. By Lambda-CDM's predictions, there simply hadn't been enough time for so much mass to assemble into such well-organized structures. One team of researchers calculated that some of these massive early galaxies were so improbably large for their cosmic age that their existence challenged the standard model at something like the 6 sigma level. 6 sigma means the probability of this happening by chance within the standard model is 1 in a billion. 1 in a billion. Scientists started calling them impossibly early galaxies, which is obviously not technically accurate. They clearly exist, so they are possible. But the name captured the scientific shock. Now, this discovery alone could have multiple explanations. Maybe star formation in the early universe was more efficient than models predicted. Maybe dark matter behaved differently in the early universe. Maybe feedback processes, the way supernovas and black holes influence their environments, worked differently then. Scientists began proposing modifications to Lambda-CDM, tweaks and adjustments that might explain the early galaxies without completely overturning the model. But then more data came in, and the situation got considerably stranger. This next piece of the story predates James Webb, but JWST made it sharply worse. It's called the Hubble Tension, and it's been building for years. The Hubble constant is the rate at which the universe is expanding. It tells you how fast galaxies are receding from us per unit distance. It is one of the most fundamental numbers in cosmology. There are two main ways to measure it. The first way, measure it directly. Look at objects in the nearby universe, galaxies, stars of known brightness, and measure how fast they are moving away from us. This is called the local measurement. The second way, calculate it from the cosmic microwave background. Use the pattern of the CMB to reconstruct the conditions of the early universe. Run the physics of Lambda-CDM forward to today, and predict what the Hubble constant should be. This is called the early universe measurement. If Lambda-CDM is correct, if our model of the universe is right, these two measurements should agree. They are measuring the same thing, the expansion rate of the universe, just in different ways. They don't agree. They disagree significantly, and the disagreement has been growing as measurements have gotten more precise. The local measurement gives a Hubble constant of about 73 kilometers per second per megaparsec. The early universe measurement gives about 67 kilometers per second per megaparsec. That's a difference of about 8 to 10%, which sounds small, but at the precision of modern measurement, where each of these numbers has very small error bars, this disagreement is statistically enormous. Statistical analyses put the tension at somewhere between 4 and 6 sigma. 4 to 6 sigma. Remember, 5 sigma is the standard threshold in physics for declaring something a discovery rather than a fluke. A 5 sigma result means the probability of it being a coincidence is about 1 in 3.5 million. The two measurements of the Hubble constant disagree at that level. The simplest explanation that one set of measurements is wrong due to some systematic error has been exhaustively checked and rechecked. Multiple independent teams using different methods, different instruments, different objects have converged on the same disagreement. James Webb was explicitly used to try to resolve the Hubble tension, to check one of the most important rungs of the distance ladder, the chain of measurements that builds from nearby stars to distant galaxies. It made things worse. JWST's measurements confirmed and sharpened the local Hubble constant measurements. The disagreement with the CMB-based measurement didn't go away. It stayed. It got cleaner, harder to attribute to measurement error. The Hubble tension is real, and if it's real, it means Lambda-CDM is wrong. Not slightly wrong. Fundamentally wrong in some way we don't yet understand. Something is happening in the universe, either in the early universe or in how the universe has evolved, that our current model does not capture. Something is missing from our physics. And then came the observation that triggered the most extraordinary conversation in cosmology. Here is where we need to be very careful and very precise, because this is a story still unfolding. The data is real, the observations are real, but the interpretation, and this is crucial, the interpretation is still being debated fiercely. What James Webb detected, in aggregate, is a pattern of anomalies, several different observations that individually might be explainable within modified versions of Lambda-CDM, but together, all pointing in the same direction at the same time, paint a picture that a growing number of theorists are willing to say out loud. Something touched our universe from outside. Let me walk you through the specific observations. First, the large-scale structure anomalies. JWST has been conducting deep field surveys, staring at small patches of sky for long periods, collecting light from incredibly distant galaxies. And in these deep surveys, the distribution of galaxies, how they cluster, how they're connected in the cosmic web shows statistical patterns that Lambda-CDM does not predict. The clustering is slightly wrong, not dramatically wrong, but statistically significantly wrong. There is a subtle excess of structure in certain configurations, alignments of galaxies and galaxy clusters across vast distances that should not be as coherent as they appear. Some theorists have pointed out that these anomalous alignment patterns are consistent with what you might expect if a bubble collision in the early universe had deposited a preferred direction, a slight asymmetry into the fabric of our spacetime. A bubble collision with another universe. Second, the cold spot. This is not a new observation. The cold spot was originally detected by NASA's WMAP satellite and confirmed by the Planck mission. It is a region in the cosmic microwave background, the oldest light in the universe that is significantly colder than it should be, about 0.00015 degrees Kelvin, colder than the average. which sounds tiny but is statistically enormous given the uniformity of the CMB. The cold spot covers an area roughly 13 times the size of the full moon in the sky, and it sits in a direction where there is also a supervoid, the largest known void in the universe, containing almost no galaxies, about 1.8 billion light-years across. Various explanations have been proposed, most of them conventional, most of them unsatisfying. But one explanation has been circulating since it was first proposed by scientists including Laura Mersini-Houghton in the mid-2000s, and it has never been fully refuted. The cold spot could be the imprint of a collision between our universe and another universe in the multiverse. When bubble universes collide, the mathematics of eternal inflation predicts specific signatures in the CMB of the surviving universe: a circular pattern of temperature variation, a disk of slightly altered density, in some models a cold region. The cold spot looks exactly like what those models predict. JWST has now returned new data on the structure of the region surrounding the cold spot, the three-dimensional galaxy distribution in that region, the statistical properties of matter clustering around the supervoid, and the data is anomalous, consistent with several conventional explanations, none of which fully fit, and consistent at a level that has made serious theorists sit up with the bubble collision hypothesis. Third, the optical depth anomaly. This is technical but important. When light from very distant sources travels through the universe to reach us, it passes through gas and plasma and gets partially absorbed and scattered. The amount of scattering is called the optical depth, and JWST has measured the optical depth of the universe in more detail and over larger scales than was previously possible. In certain directions, certain patches of the sky, the optical depth is subtly but significantly different from what Lambda-CDM predicts. The universe appears to be slightly more or less transparent than it should be in ways that are directionally asymmetric. Directionally asymmetric means the universe looks slightly different depending on which way you look, which should not happen in a universe that is smooth and the same in all directions, as Lambda-CDM assumes. The asymmetry is small, but it is there, and it has a direction. It points along with several other anomalies toward the same general region of the sky, the same general direction as the CMB cold spot. Fourth, anomalous galaxy alignments at cosmic scales. JWST's deep field surveys have now mapped galaxy distributions at redshift distances that were previously inaccessible, and there is a coherence to the orientation of galaxies across scales so large that they should not be causally connected. Galaxies, hundreds of millions of light-years apart, are aligned in ways that have probability estimates within standard cosmology of less than 1 in 10,000. 1 in 10,000 is not proof, but it is a flag. A flashing red light saying, "Look here, something unusual is happening here." Taken individually, each of these anomalies has a conventional explanation, or at least a possible conventional explanation. Taken together, all pointing in the same direction, all at odds with Lambda-CDM, all consistent with the specific mathematical predictions of bubble universe collision models, they form a pattern. And that pattern has a name. Some cosmologists are now calling it the bubble collision signal. Let's go deeper into the physics, because this is where things get genuinely extraordinary. In eternal inflation, our universe formed when a region of the inflating quantum field, the inflaton, underwent a phase transition. The energy of the inflaton decayed from its high energy state to a lower energy state. That transition released an enormous amount of energy which we experienced as the Big Bang. The region where this transition happened is our bubble universe. Outside our bubble, inflation continues. Other regions undergo their own phase transitions and become other bubble universes. This is the inflationary multiverse. Now, these bubbles don't just float apart peacefully. They are expanding into the inflating background. And the mathematics says that two expanding bubbles can collide. What happens in a bubble collision? The mathematics, and this was worked out in detail by physicists including Matthew Johnson, Hiranya Piris, and others, predict specific, calculable effects on the CMB of the surviving universe. First, the collision creates a disk, a roughly circular region in the CMB that has different statistical properties from the rest. The temperature pattern in this disk differs from the surrounding CMB in a specific way. Second, the collision creates a preferred direction, a slight breaking of the perfect symmetry that Lambda-CDM assumes. The universe would be slightly different depending on which direction you looked, which is exactly the directional asymmetry that multiple observations have found. Third, depending on the specific parameters of the collision, the relative sizes and speeds of the bubbles, the nature of the physics in each bubble, the collision can produce either a hot spot or a cold spot in the CMB. A cold spot, exactly like the one we observe. Fourth, the collision would deposit extra energy, or a deficit of energy, in a roughly disc-shaped region of the early universe. This would affect how matter subsequently clustered in that region. It would produce subtle anomalies in the large-scale structure of galaxies in that direction. Anomalies like the ones JWST is seeing. The extraordinary thing is this. These predictions were made mathematically, precisely, quantitatively before the JWST data, before the deep field surveys, before the optical depth measurements. The theoretical predictions, derived purely from the mathematics of eternal inflation and bubble collision physics, were compared to the data. And the data fits. Not perfectly. Not at the level that makes every physicist nod confidently and say, yes, that's it. But well enough. Consistently enough. In enough independent ways. To make the hypothesis that our universe collided with another universe a genuinely serious scientific proposal. Not a fringe idea. Not a crack theory. A peer-reviewed, mathematically grounded scientific hypothesis that fits multiple independent lines of observational evidence better than the standard model does. Now, and this is absolutely crucial to understand, the scientific community is not unified on this. Science doesn't work through unanimous agreement. It works through debate, through challenge and counter-challenge, through the slow accumulation of evidence and the willingness to change your mind when that evidence demands it. And right now, the debate is fierce. Let's look at both sides honestly. The case for taking the bubble collision hypothesis seriously. The Hubble tension is real and unresolved. No modification to Lambda-CDM has convincingly explained it. The tension has only grown as measurements have improved. This means Lambda-CDM is definitely missing something. The early galaxy problem is real. JWST found too many massive early galaxies. No conventional explanation has fully accounted for this. Our models of early structure formation are wrong in some way. The CMB cold spot has never been convincingly explained by conventional physics. Every proposed conventional explanation has problems. The bubble collision explanation makes a specific prediction the existence of a large void in that direction, and there is indeed a large void there. The directional asymmetries found in multiple datasets from the CMB, from galaxy surveys, from JWST, all point toward the same region of sky. This coherence across independent datasets is striking. The bubble collision models make testable, quantitative predictions. They are falsifiable. They are being tested. And so far, they have not been falsified. The case for skepticism. The anomalies, while real, are all at the 2 to 4 sigma level individually. None is individually convincing. It is possible that we are suffering from confirmation bias, looking for a pattern in noise and finding one because we want to. Cosmology has a history of apparent anomalies that turned out to have mundane explanations. The axis of evil, an alignment of features in the CMB that seem significant, may be partly explained by local contamination from our own galaxy. Alternative explanations for the Hubble tension modifications to dark energy. New physics in the early universe haven't been ruled out and don't require a multiverse. The early galaxy problem might be solved by modifications to our understanding of star formation efficiency in the early universe, without requiring any new physics. And fundamentally, the multiverse is still not directly testable. Even if the bubble collision hypothesis is correct, it doesn't prove that there is an entire landscape of universes. It proves one collision with one other universe. The step from that to an infinite multiverse requires additional theoretical assumptions. These are serious objections. They deserve serious engagement. And the scientists pursuing the bubble collision hypothesis are engaging with them. The key papers have been submitted for peer review. Datasets are being independently analysed. Different groups are approaching the observations from different angles. This is science working as it should. Now, I want to spend some time on something that the headline of this video promises. What does it mean to shatter every model built since Einstein? This requires some nuance, because Einstein's work itself is not being shattered. General relativity remains, as far as all tests have determined, spectacularly correct. Every measurement that can be made of strong gravitational effects, gravitational waves, black holes, the large-scale structure of space-time, general relativity, passes them all. What is being challenged, what JWST's observations are putting pressure on, is the cosmological model that was built on top of general relativity. Lambda-CDM, the specific picture of how the universe began, evolved, and is structured today. The specific values of parameters, the specific assumptions about initial conditions. Think of it this way. Einstein gave us the grammar of the universe, the rules by which space-time operates. Those rules appear to be correct. But Lambda-CDM is a specific story told in that grammar. A story about this particular universe, with these particular initial conditions, with this particular content of matter and energy, evolving in this particular way. And that story may be wrong, not in the grammar, in the plot. The bubble collision hypothesis doesn't violate general relativity. It uses general relativity. The mathematics of bubble universes and their collisions is derived from Einstein's equations. What it violates is the assumption built into Lambda-CDM that our universe is all there is, that its initial conditions were set by a single Big Bang, that it is, in a meaningful sense, a closed system. If our universe collided with another universe, if the cold spot and the anomalies are what some theorists think they are, then the initial conditions of our universe were influenced by physics outside our universe, by another spacetime, by a different cosmic history. And Lambda-CDM has no room for that. Lambda-CDM assumes our universe started clean, with initial conditions set by a single inflationary episode, undisturbed by external influences. If that assumption is wrong, the model built on it must be rebuilt. And rebuilding it means incorporating the multiverse into mainstream cosmology, not as a philosophical speculation, not as a thought experiment, as a physical reality that leaves measurable signatures, as a scientific framework with testable predictions. That is what shattering every model built since Einstein means. Not disproving the equations, expanding the scope of what the equations describe. It means the universe is bigger, stranger, and more wildly complex than even the most ambitious cosmological models assumed. Science does not end with a single paper or a single telescope. It evolves, it accumulates, it argues with itself, and eventually reaches conclusions. So what happens next? What are scientists doing to follow up on these observations? What instruments, what missions, what theoretical work is going to determine whether the bubble collision hypothesis stands or falls? Several things are already in motion. First, more JWST data. James Webb has a planned lifespan of at least 20 years. It is still in the relatively early stages of its scientific mission. The anomalies we discussed are based on the first few years of data. As JWST continues to survey the deep universe, conducting more deep field observations, mapping the large-scale structure in more directions, measuring more galaxy spectra, studying the properties of the early universe in more detail, the statistical picture will either sharpen or dissolve. If the directional anomalies persist and strengthen, as more data comes in, the case for something unusual in that direction becomes more compelling. If the anomalies wash out, they were probably noise. JWST's planned observing programs include dedicated surveys of the CMB cold spot region, detailed mapping of the galaxy distribution in and around the supervoid, studies of the large-scale structure at high redshift in multiple directions to test for directional asymmetry. This data will be decisive. Second, the Euclid mission. The European Space Agency launched the Euclid Space Telescope in 2023. Its mission is specifically to map the large-scale structure of the universe with unprecedented precision. Over its mission lifetime, Euclid will map the distribution of more than 1 billion galaxies across a significant fraction of the sky. This galaxy map will allow extraordinarily precise measurements of how matter is clustered at different scales. It will test the predictions of Lambda-CDM and its competitors with new levels of statistical power. It will directly address the question of whether there are directional anomalies in the large-scale structure. If the bubble collision hypothesis is correct, Euclid should see specific signatures in the galaxy distribution, statistical patterns that match the theoretical predictions, in the direction of the cold spot, and potentially in other directions where other bubble collisions may have occurred. Third, next-generation CMB experiments. The Simons Observatory in Chile, the CMB S4 experiment. These ground-based telescope arrays will measure the polarization of the cosmic microwave background with extraordinary precision. The bubble collision models make specific predictions about the polarization pattern of the CMB in the affected region. Not just the temperature, which is what most previous measurements focused on, but the polarization, the direction in which the electromagnetic waves of the CMB are oriented. These polarization measurements are technically very challenging, but they are potentially the clearest test of the bubble collision hypothesis. The predicted polarization signature is specific enough that it would be very difficult to explain by any conventional mechanism. If the polarization data shows what the bubble collision models predict in the right location, with the right pattern, that would be extraordinary. Fourth, theoretical development. Dozens of theorists around the world are now working on refining the bubble collision models, making the predictions more precise, exploring different parameter spaces, understanding what range of collision geometries and energies could explain the specific anomalies JWST has seen. At the same time, theorists working within conventional cosmology are also working hard, developing modifications to Lambda-CDM that could explain the same anomalies without requiring a multiverse. Exploring different models of dark energy, different theories of early universe physics, different structures for the inflationary potential. This theoretical competition is healthy. It is how science makes progress. The model that makes the best, most precise, most falsifiable predictions, and whose predictions are confirmed by observation wins. We may be years away from a verdict, or we may be months away from a decisive observation. Let me ask you to set aside skepticism for a moment. Let me ask you to sit with the question, what if it's true? What if the bubble collision hypothesis is confirmed? What if future data from JWST and Euclid and CMB S4 converges on the conclusion that yes, our universe was struck in its earliest moments by another universe? That the cold spot really is a bruise? That the anomalies really are fingerprints of an outside universe pressed against ours? What would that mean? It would mean first and most simply that we are not alone, not in the sense of aliens, but in the cosmic sense. Our universe is not the universe. It is a universe, one among many, possibly one among infinitely many. Every philosophical and religious tradition that has ever existed has assumed, explicitly or implicitly, that the cosmos, the totality of everything, is this. What we can see, what we can in principle measure, what obeys the same laws of physics we understand, that is the universe. The whole thing. That assumption would be wrong. There is more. There is other. There are places where the constants of physics are different, where atoms might not exist as we know them, where gravity might be stronger or weaker, where stars might burn differently, where time might flow at a different rate. We know this because physics here, in our bubble, bears the marks of a collision with one of those other places. Second, it would answer the fine-tuning problem, definitively. If there are truly an enormous number of universes, each with different physical constants, then our universe's suspiciously life-friendly constants are not miraculous. They are inevitable. In an infinite landscape of universes, every combination of constants will exist somewhere. We live in this one, because this is the one where we can live. The cosmic mystery that philosophers and theologians have wrestled with for centuries, why do the laws of physics seem designed for us, would have a clean, scientific, non-mysterious answer. Because most universes don't work for us. This one does. So here we are. Third, it would transform our understanding of the Big Bang. The Big Bang would no longer be the absolute beginning. It would be a transition, a phase change in a quantum field triggered by conditions in an eternal, inflating background. Our universe's history would extend before the Big Bang into the physics of that background, into the dynamics of bubble nucleation and collision. The question, what happened before the Big Bang, which physicists have long said is meaningless, since time itself began at the Big Bang, would become meaningful again. What happened before was the inflationary multiverse. What happened before was other universes. What happened before was a bubble collision that set our initial conditions. Fourth, it would open the extraordinary, remote, almost unimaginable possibility of eventually understanding other universes, if we can read the signature of a bubble collision in our CMB, if we can measure the specific properties of the region of our space-time that was affected by contact with another universe, then, in principle, we can learn something about that other universe. Not much. The information encoded in a bubble collision signature is limited, but some. We could potentially infer something about the physics of the other universe, about its cosmological constant, about its inflationary parameters, about whether it was hospitable to complexity and life or a dead, structureless void. We would be, in the most literal possible sense, learning about another universe. That is almost too extraordinary to contemplate, and yet the mathematics allows it. The observations, tentatively, suggest it. And science has a long history of making the almost unthinkably extraordinary into the mundane routine of understanding. I want to step back now from the physics and the data and the telescopes, and I want to talk about what this means for us, as humans, as the species that is looking up at the sky and asking these questions. There is a thread that runs through all of human history, a thread of curiosity, a thread of wanting to know. Every human civilization, in every part of the world, looked up at the sky and wondered, what are those lights? What is this cosmos we find ourselves in? Are we alone? Is there something beyond what we can see? Different cultures gave different answers. Myths, gods, cycles of creation and destruction, sacred cosmologies that placed humanity at the center of a meaningful universe. And then came science, and science began, methodically, patiently, to peel back the layers of appearance and find what was underneath. The Earth is not flat. The Earth is a sphere. The Earth orbits the Sunday. The Sun is one star among hundreds of billions in the galaxy. The galaxy is one among hundreds of billions in the observable universe. The observable universe is not the whole universe. Each step outward was a revelation. Each step made us feel smaller, and each step, paradoxically, made us feel more remarkable. Because we are the part of the universe that looks at itself and understands what it sees. We are matter that has organized itself to the point where it can comprehend the laws that govern matter. And now, standing at the threshold of the most extraordinary possible discovery in human intellectual history, we are potentially learning that the universe itself is not the universe. That the cosmos is immeasurably larger, more varied, more strange, more magnificent than anything our myths or our scientific models imagined. If the bubble collision hypothesis is confirmed, if James Webb has genuinely detected the fingerprints of another universe, then we are standing at a moment unlike any other in human history. Not the discovery of a new continent, not the discovery of a new planet, not even the discovery of life elsewhere in our universe. The discovery that our universe is one room in an infinite mansion, that the door of our room bears, in the pattern of the oldest light we can see, the marks of a collision with another room, that somewhere in a space-time we cannot visit, cannot communicate with, cannot see other laws of physics govern other forms of existence. Or perhaps not. Perhaps the anomalies will resolve into mundane explanations. Perhaps Lambda-CDM will be patched and survive. Perhaps the bubble collision signal will fade as more data comes in. Science demands that we hold that possibility equally. We must not want the extraordinary answer so badly that we convince ourselves the evidence is there when it isn't. But the evidence is there, tentatively, persistently, pointing in the same direction across multiple independent datasets, from the most powerful telescope humanity has ever built. And that is worth taking seriously, worth examining carefully, worth following wherever it leads. Because wherever it leads, even if it leads to a mundane conventional explanation, the journey itself deepens our understanding, sharpens our instruments, refines our theories, pushes us closer to whatever the truth actually is. And if it leads where the current data tentatively suggests it might lead, then we will have done something that no creature in the history of life on Earth has ever done before. We will have seen beyond our universe. We will have detected the existence of something outside the totality of everything we have ever known. And we will never, not in any possible sense, be able to see the cosmos the same way again. Let me be completely honest with you about where things stand. James Webb has detected a collection of anomalies, real, statistically significant anomalies that the standard model of cosmology Lambda-CDM struggles to explain. Too many early massive galaxies, a persistent Hubble tension that has only gotten sharper with JWST data, directional asymmetries in the large-scale structure, anomalous clustering patterns, all broadly consistent with predictions from bubble collision models. The bubble collision hypothesis that our universe collided with another universe in the early cosmic epochs is a genuine, mathematically grounded, peer-reviewed scientific proposal. It makes testable predictions. It has not been falsified, and it fits the anomalous data better than the standard model does. But it has not been confirmed. The anomalies are individually explainable with difficulty by modifications to conventional cosmology. The statistical case, while suggestive, is not yet decisive. More data is coming. The debate is ongoing and genuinely open. What is not in doubt is that Lambda-CDM is under serious pressure, that the standard model of cosmology is imperfect in ways that current data is revealing. That's something, whether it is a bubble collision, a modification to dark energy, new physics in the early universe, or something entirely unanticipated, is missing from our current picture. Physics is at a genuinely exciting, genuinely unsettled moment. And James Webb sitting out there at L2, 1.5 million kilometers from Earth, pointing its gold mirror at the oldest light in the universe, is the instrument that is making that unsettledness visible. That is remarkable. That is science working exactly as it should. Not delivering comfortable confirmations of what we already thought we knew, but finding the cracks, illuminating the edges, pointing at the places where our understanding breaks down and saying, "Here, look here, we don't understand this yet." Because in those cracks, in those anomalies, in those places where the data doesn't fit the model, that is where the next revolution lives. That is where the next Einstein will find the question that, once answered, changes everything. So here we are, a species that started on one small planet around one ordinary star in one corner of one galaxy. A species that, a few thousand years ago, didn't know the sun was a star. That, a few hundred years ago, didn't know there were other galaxies. That, a few decades ago, didn't know the universe's expansion was accelerating. And now sitting in that planet, around that star, in that galaxy, we have built a machine and sent it into space. And that machine is looking at light so old it was emitted when the universe was barely formed, looking at the oldest patterns written in the fabric of space-time. And in those patterns, possibly, tentatively, extraordinarily the marks of another universe. If that doesn't make you feel something deep and strange and magnificent, I don't know what will. We are incredibly small, and we are seeing across billions of light years to the edge of what is knowable. We are temporary, and we are wrestling with questions about the nature of eternity. We are one species on one planet, and we are potentially detecting the existence of other universes. I said at the beginning of this video, nothing about our understanding of reality may ever be the same again. I meant that. Not because the evidence is conclusive, but because the question has been asked seriously, with real data, with real mathematics, in the pages of real scientific journals. Is there something else? Is there more? Is our universe just one? James Webb is looking, and it is finding anomalies, hints, patterns that don't fit. And in science, that is always where the most important stories start. Stay curious. Stay amazed. And the next time you look up at the night sky, remember that what you are seeing is not the whole story. Not even close. The whole story may be bigger than we have ever dared to imagine.